My name is Augustus Pacigalupi, and this is a short talk I gave at the 2012 Joint Conference of the American Society of Cybernetics and the Bateson Idea Group on July 11th. It's an introduction to a portion of a project called synthetic cognition. The larger project will build and empirically test synthetic cognition using a hypothesis for adaptive systems I call refinement, the subject of this short talk. So this talk is split into 4 parts. Part 1 is an informal definition of refinement. Part 2 is an intuitive and formal definition of complexity. Part 3 is an intuitive and formal definition of adaptive work. And Part 4 concludes on how complexity and adaptive work relate to provide a formal definition for refinement. So, Part 1. In general, refinement is an empirical measure of adaptive or fitness potential for an intentional system, such as embodied animal cognition. More specifically, but still an informal definition, refinement is a noun, and it's a process whereby a system increases its average relevance, to be defined rigorously throughout this talk, increase its average relevance to its surroundings by increasing its own internal capacity to resolve internal disorder, which is the result of increased relevance, the same relevance as mentioned before, into a higher order internal structure able to increase capacity to do useful work. So, in essence, it's the capacity to do more adaptive work with the same resources in a dynamic and complex environment. Now, it's important to note that refinement is a test for cognition, not cognition itself. Designs for a buildable and testable synthetic cognition are available on my website, iforam.org. This short talk focuses on the test, the nature of the theory, and the hypothesis and what's being tested for. So Part 2, complexity. So to adapt to one's environment, an agent must embody structural complexity that is relevant to its environment. This is analogous to learning. The brain is plastic, we know, and that plasticity is an internal structure that embodies complexity. So what is the nature of this complexity in living systems? Living systems do not maximize order, nor do they minimize disorder. Living systems thrive somewhere in between. So, for example, down below, the figure grounds A, B1, B2, and C. A and C are what I call death states. In other words, A is undercoherence, and C is overcoherence. And life can't exist here. A is perfectly random. You could see, for example, analogously, all the pixels in figure A are random. They're completely uncorrelated. Whereas in C, they're completely coherent. In other words, they completely correlate with each other. And this relates to the parabola above, points A and C, on a one-dimensional spectrum of order. So you have complete disorder, which is complete randomness, and complete order, which is complete coherence. Now, the body isn't the mind nor the body is completely coherent, and nor is it completely decoherent. It has to be somewhere in between. And as Bateson has said before, life requires that its embodied complexity embody a difference that makes a difference. So all we're showing now with points B1 and B2 up in the parabola is a y dimension of complexity, so that we move above the purely one-dimensional order versus disorder and move into the realm of complexity, into a more distinct figure ground, the ability to embody distinctness. So in order to move this project forward, requires a paradigm shift and a different understanding of information that's inspired by the figure grounds and the parabola just discussed. So the paradigm shift must understand that information in general is not discrete and independent, as indicated by C in the previous slide, complete coherence. It's not ones and zeros as in our digital computers. It is both distinct physical events and their interrelations simultaneously. So, for example, we have some ripples on the water. Each drop is distinct, but also they have ripples that emanate out from each epicenter of the drop, and those ripples are also embodied in water. They superimposed amongst the ripples of other drops to embody the interrelationships between each drop. So we have both the distinct events and their interrelations simultaneously. Now, to understand and implement complex dynamic systems in practice, such as cognition, we must employ more appropriate analogies. So for example, activity in the brain via local field potential ion gradients and aphaptic coupling is much more like these ripples than existing models have even begun to represent. So let's extend the analogy and see where that leads. So here we have the ripple analogy extended. We've just multiplied the ripples, and we can imagine just looking at a pond while it rains, and each drop will in reality would be more or less random in terms of the time it hits the water relative to some other drop and the location. But for the sake of argument, let's imagine that it's not so random, that in fact each drop falls in a particular place above chance, and that each of those locations receiving a drop above chance would then correlate with another drop in time above chance. So what we have is essentially pairs of drops falling somewhat in the same place and more or less at the same time. Not just pairs, but say 3 at a time. Of course, this wouldn't happen in reality for drops on a pond, but it does illustrate complexity. And to understand complexity, now imagine that some of these initial groupings begin to co-occur with other groups, groups of groups, patterns of patterns. An increasingly rich distinctness emerges from a single physical substrate. Now we can even see groups of groups of groups coexisting simultaneously in the same common physical medium. And the orders of this accrued complexity can increase even further. We can have groups of groups of groups of groups. So what we have now are nested interrelations of distinct physical events that become more complex without consuming more resources. In contrast, the discrete and independent symbols in digital machines do not interrelate. Such discrete state machines consume exponential resources to simulate interrelations, not be interrelations. So for example, digital computers, in order for them to create relationships between states, they have to employ ever more discrete states. Unlike our example here with the drops on the water, which embody both the distinct events and their interrelations simultaneously. And that's what we're formalizing with this definition of complexity. Complexity alone is not enough to measure the physical dynamics that make these higher order interrelations possible, because like entropy, complexity is a state variable. Complexity says nothing about how the system achieved a certain state or what states will tend to emerge. For this, we need a path function, namely work. To understand how complexity can contribute to physical work, imagine nodes like tuning forks tuned to diverse frequencies. This example shows specific nodes being stimulated by acoustic patterns from the environment. Like the water ripples, this interference pattern embodies both distinct events and their interrelations simultaneously. So what we have here are the magenta nodes that are each tuned to a frequency indicated by the frequency in hertz above each node, and when stimulated by a similar frequency from the environment, they vibrate like a tuning fork, creating ripples in their shared interstitial medium, which could be water or electromagnetic field, etc. Now, that's all fine and good, but without memory, this interference pattern may just as well be transient noise. But as the pattern persists via stimulation from the environment, interconnections are formed between repeatedly stimulated nodes along these more salient interference patterns. This is memory. For example, this remembered pattern is C major. Each of these frequencies is near one of the frequencies within the chord C major, for example, the notes C, E, and G. Now, for actual implementations of how these interconnections are created, you can see my website, i4m.org, and I'll also do a follow-up video shortly that will describe the technical implementation of these connections. But for now, just understand that connections do form, which biases the behavior to enable more complex work, and this bias is structure. Here is another distinct remembered pattern stimulated by the environment, in this case E minor. Like the C major pattern, such a system harvests the sparse order from within the interference pattern. Now, because it's the same matrix and the same medium, in other words, both the C major example and the E minor example from before have the same tunings of nodes, the same geometric distribution, they can be the identical matrix. And because of this, the two distinct patterns can co-occur and superimpose into a higher order pattern. In this case, C major and E minor coexist to become C major 7th, a coincident hierarchy. Now, this is what's missing from our understanding of real-world systems. Superposition of distinct yet interrelated patterns embodied in a physical common medium, not just discrete and independent symbols that must be manipulated by fixed rules, themselves implemented via discrete symbols. Now, C major and E minor are still distinct, but now they can be related as well at a higher level of complexity. This is embodied complexity able to do useful higher order work. So what we have are interconnections over here on the right based directly on node coactivity, and it will usefully structure the network to do more work when patterns from the environment reoccur. And this is adaptive work potential and the foundation for a process of assimilating ever higher order complex and adaptive behaviors given fixed resources. This informed and complex structure will increase work efficiency in recognizing formally learned patterns. So with the work equations, all we're showing is that on the left, without the interconnections, the nodes may be stimulated, but because of the circuitry within each primary node, they will not create as much real power, which is indicated by current times voltage down in the equation I times V. Therefore, the integral of real power equaling work will be less than the biased network that has been structured or informed, literally formed by patterns in the environment, so that the behavior of each node will be such that they will synchronize when a pattern reoccurs, and they'll respond more vigorously and use available resources more efficiently, thereby doing more work with the same amount of resources. And this brings us to a formal definition of refinement, where the x-axis is time and the y-axis is relevance, which is defined as complexity of nodal behavior times the work done by each node divided by the total energy consumption of the system. Okay, so what that means is, put in other words, that given fixed energy input, relevance increases when more adaptive work can be done because an agent's internal structural complexity has increased. And not just the structural complexity, as stated before, hasn't just increased arbitrarily. It's that complexity has been biased by patterns in the environment. So there's what Terence Deacon in his book Incomplete Nature calls intentional relationships, and that's intentional with an E. So it's EN, intentional. And I'll say more about this in the next video. But for now, what we can say is that if the system does show more relevance over time, and again, there's a lot to say about this diagram, why it oscillates, etc., that I don't have time to get into now. But essentially, the trajectory of that oscillation, the overall relevance over time, is refinement. So that as relevance increases, there's an average trajectory that I'm defining as refinement. So an increase in refinement is empirical evidence that perceptual and learning capacity have accrued. Now, I know that was a lot of information, so I definitely look forward to your questions and comments here and also on my website, which is i4am.org. There's a lot more detail on my website, but please feel free to ask any specific questions, and I can address them directly, or at the very least send you in the right direction. So thank you very much.